This is video 3 of section 3, Convolutional and Pooling Layers. In the previous video, we defined a layer in Keras and implemented a classical neural network layer. In this video, we will talk about what are convolutions and pooling, how do they work in Theano, and we will finish this section reviewing how to use them in Keras. Convolutions can be understood as a sequence of sliding and projection operations. In this slide, we can see the definition of convolution for one-dimensional signals and an illustration for the two-dimensional case. The sliding here is defined by this displacement t, and the projection is just the inner product between two functions. For the case of vectors, the inner product is just the vector inner product for the case where the filter, which is the small image in the middle, and the region in the green image where it overlaps. These are the results. You can check that these operations are correct by yourself, but make sure you do that to have an intuition of how convolutions work. Pooling is simply downsampling an image or a vector. Especially in max pooling, we do that by taking the largest number in an image neighborhood. The largest numbers in a convolved image are those where the convolutional filter found best matching inputs. From this point of view, we can think about convolutions as feature matching and pooling as best match detection. The combination of both convolutions and pooling is what gives convnets such a good shift invariant representations. This is why we can use convnets to detect objects in an image without caring too much about the size of the object in the image. Let's move to our IPython notebook and see a convolution example in Theano. In our example, we will convolve the image of Lina with a random filter using Theano conv2d. In these first two lines, we visualize our image. In this last line, we define the input image for Theano as a tensor of 4 dimensions. The first one is the batch dimension for the case of parallel processing of several images. Here we are going to use only one image. The second dimension is the number of channels. In this case, 1, since we have a grayscale image. The last two are the number of rows and columns of the image. The second tensor will be our filter. It's 4 dimensions as well. The first dimension is the number of channels in the output image. The second is the number of channels in the input. And finally, the last two are also the number of rows and columns in the filter. And those two are always like this, smaller than the input image. For deep convolutional neural networks, they are usually 3 by 3 or 5 by 5. I've seen up to 11 by 11, but 3 by 3 is the most common nowadays. Here's our Theano code to calculate convolutions. We start by defining our tensors of 4 dimensions with Theano, and we use conv2d from the nnet module to do the convolution and the pooling operations. Here we are defining our convolution as a symbolic expressions and compiling the function. All the parameters here are obvious, but this border mode, for valid convolution mode, only the projections where the filter is completely inside the image are considered. Another important border mode option is full, where the projections in the border with partial overlap between the filter and the input are also kept. Just to illustrate this border mode, I will first print the shape of the input image. Later, I will print the shape of the output image as well. In this line, we calculate the output image. These other lines are for visualization, to show the original input side by side with the output. Using a random filter, the output of the convolution is a contrast-reduced image. Some filters implement edge detections, for example, In supervised learning with convnets, the job of the backpropagation algorithm is to learn the appropriate filters to classify the image. Finally, using Keras, let's implement a convolution followed by a max pooling layer with pool sizes of 8 by 8. In practice, pool size is usually 2 by 2, but let us exaggerate a little bit just for fun and for educational purposes as well. So here's our Keras model, starting with a sequential and then adding both the convolution and max pooling layers. I hope you remember that from our very first Keras example, back in section 1. We call model.predict and use the input image to calculate from here to here. Again, we use matplotlib to visualize our results. We can see that the details of the input image was almost completely filtered out in the output. Just the essence of the input image remains. And this ends our video. Here we investigated what are convolutional and pooling layers. We finished implementing convolutions in both pure Theano and Keras. In this section, we saw how Keras works behind the scenes and investigated the most basic but fundamental types of deep learning layers, namely fully connected or dense layers and convolutional and pooling layers. In the next section, we will cover advanced convolutional architectures and the cats versus dogs dataset.